Hello and welcome to this World Summit presentation. My name is Jörg Bornemann. I'm leading the Build Tools team at the Qt company. In a former life, I've worked on virtual reality applications, computer vision, then industrial automation. And I started working on Qt and surrounding projects in 2007. Much work was related to build systems, QMake, contributions, JOM, QBS, now CMake. The title of the talk is From QMake to CMake, Recipes for Converting QMake Projects to CMake. The agenda. We will have first a quick look at how to automatically convert QMake projects to CMake. Then we'll answer the question on how building is done with CMake and how build configurations are managed. Then we'll walk through the skeleton of a Qt application project. After that, we will explore common tasks that arise when writing a Qt project. How do we do things in CMake that we did in QMake? Finally, we will work through the task of installing a project. If you have any questions during the talk, please type your questions into the chat window, and I will answer them either during my presentation or afterwards. First of all, I want to emphasize that QMake is still supported for your user projects. Just Qt itself doesn't build with QMake anymore. There are no immediate plans to drop QMake support, so that's good news. Still, for new projects, we highly recommend to use CMake. There's much to gain from that. For this talk, I'll assume that you're experienced with writing QMake projects. We'll walk through some typical tasks and look how they are done in QMake and how we could do them in CMake. So without further ado, let's dive right into it. There's automatic conversion aid for converting your QMake project. When porting Qt from QMake to CMake, we wrote a conversion program, Pro to CMake, in Python. It was heavily tailored towards converting Qt itself and not so much to convert user projects. But by now, Pro to CMake has been turned into something that can convert user projects too, and its name is now QMake to CMake. You would install QMake to CMake with Python's package manager pip. Just run pip install QMake to CMake, and then it should magically work. And you will get two executables, QMake to CMake _all and QMake to CMake without the _all suffix. With the QMake to CMake _all program, you can convert the whole project tree. You have to pass a project root directory to it, and you have to specify a minimum Qt version. So for instance, you can specify min Qt version 6.4. Then CMake functions can be used by QMake to CMake that are not available in 6.2 yet. You can also convert just a single .pro file by using QMake to CMake. You pass the .pro file to it and also the minimum Qt version. This will convert the overall project structure, but manual adjustments are still necessary. Like QMake, CMake is a build system generator. It takes a high-level description of your project and turns it into make files, for example, or Ninja build files. On Windows, we don't need JOM anymore. We highly recommend using Ninja. Ninja is fast, reliable, and cross-platform. You can list all the available generators by typing CMake-G on the command line. And this example here shows how you would configure your project with the Ninja generator and for the release build configuration. There are several built-in build configurations in CMake: release, debug, one for optimizing your program for minimum size, and one for a release build containing debug information. And you can define your own build configurations as well. To build your project, you would run CMake --build and pass the build directory, or just dot if you're doing an in-source build. Alternatively, you just run Ninja in the build directory. In QMake, we had a config value called debug and release to enable multi-configuration builds. In CMake, this requires the Ninja multi-config generator, which is also a reason why we recommend Ninja. The make file generators do not support multi-configuration builds. Multi-config support was added in CMake 3.17, and we need to specify our build configurations now in a different variable, CMake configuration types. So this shows how you would configure your project for debug and release. Beware that multi-config setups can be tricky. It's highly advised to read the Ninja multi-config page of CMake's documentation. So let's have a look at the very simple QMake application, or QMake project file for a simple application. We set the target name to my app, we set the version. This project consists of exactly one source file, main.cpp, and we want to use the widgets Qt module. In CMake, it looks a little bit more noisy, but for good reasons. The first line, CMake minimum required version 3.22, tells CMake that our project requires at least CMake 3.22. Trying to configure the project with an older CMake will result in an error. The command also tells newer CMake versions to behave like CMake 3.22. Read up on CMake policies to learn about this backwards compatibility feature. The project command declares a new project and runs some internal initialization. For example, if you're doing a cross build, then you would specify a toolchain file, and the project command takes care of loading that toolchain file. The find package call is our equivalent of qt plus equals widgets. So on this line, we load the Qt6 package. It is required that it exists. There will be an error if it's not found, and we load the widgets component of Qt6 and all its dependencies, like Qt core. Qt standard project setup is available thanks to this find package call. It runs the setup steps for a typical Qt application, like enabling mock and UIC and several platform-dependent adjustments. Qt executable creates an application target with source file main CPP, just like we saw in our QMake file. But there's a big difference to QMake. One of those project files can contain multiple targets. This is also the reason why we have to explicitly link against Qt widgets in the next line. The call to find package to pull in the widgets module is not sufficient. We also have to explicitly link against it. The target my app is linked against Qt widgets, and this thing here, the private keyword, roughly means that we do not want to expose our usage of Qt widgets to users of the my app target. This is usually not relevant for executable targets, but it's highly relevant for libraries. So let's go on a short detour about CMake usage requirements to clarify what this private keyword means. There are two other keywords, interface and public. Assume we have an executable target myapp that links against the library mylib. Mylib in turn links against the libraries foo, bar, and baz, but with different keywords in the target linked libraries call. Libraries linked with the interface keyword are linked to the so-called link interface. That means here that every library that links against mylib links against bar as well. So myapp will also link against bar, but it won't link against foo because of the private keyword here. Public is a combination of private and interface. So if we look at the effective linker command line, the libraries that appear on the linker command line when linking mylib, then we see that foo is linked because it's privately linked. Baz is linked because it's publicly linked, which means private end interface. And the linker command line of myapp, there occurs mylib because we directly link mylib privately. Bar appears because of this interface keyword, and baz appears because of this public keyword. The private, interface, and public keywords are not only restricted to the target linked libraries call, but basically any commands that take a target and set properties on it, like defines, include paths, and even sources. The common task to check for the target platform and conditionally add sources, defines or tool options, and this QMake example here adds a windows-only.cpp file if we're building for Windows. In CMake it looks like this. We check the value of the variable win32 and call the target sources command. And here we also see the private keyword. Libraries could use the interface or public keyword here to inject source files into their consuming targets. There are booleans available for every major platform: Win32, Unix, Apple, Android, iOS, and you can inspect the content of CMake system name and friends for more detailed information. Similarly common is the check for the host platform. What am I building on? In QMake, we had this QMake_host.os variable. We could check whether its value was Windows and then do something Windows specific. In CMake, quite consistently, we check for the Boolean value CMake host win32, and the Booleans to check are prefixed with CMake host underscore, just like we saw before, CMake host win32, CMake host Unix, and so on. And also the content of CMake host system name, CMake host system version, and so on can be inspected for more information about the host system. Checking for debug and release configurations. Another common task is to check whether we are building the debug version of our project or the release version. In QMake, we call the uppercase config function to ask whether debug is the active configuration in the configuration set debug release. And in this example, we have the debug build preprocessor define if we're building the debug version of our project. In CMake, we have two variables that we have to check because of the distinction between single config and multi-config builds. We have to check CMake build type for the single config case, and we have to check CMake configuration types for the multi-config case. And this makes it a little convoluted, but in your own project, you could put this into a convenience function, and the equivalent of adding a define is the target compile definitions call. We run it on the my app target, again with the private keyword, and add the debug build define. Again, libraries could use the interface or public keyword to inject preprocessor definitions into consumers of the library. A good way to structure your project in QMake and CMake is to use subdirectories. In QMake, you would use something like this. You would have a application, and that application uses a helper lib. The helper library must be built before the application to be used by the application. In QMake, this is done with the .depends key of the application subdirectory, or alternatively, one could use config plus equals ordered to force a sequential build of all subdirectories. That means in QMake we have dependencies between subdirectories. We also have code in the application subdir that tells QMake to link the application against the library. We have to define the relationship between application and library twice. Once here on the subdir level, and once within the application project itself. In CMake, things are slightly different. We still add subdirectories, now with the add subdirectory command. But there are no dependencies between subdirectories. Dependencies are defined between targets. If we look at the files at the lower level, helper lib is defined and my app is defined. Then my app links against helper lib. This is done in the last line here. And this call does not only add helper lib on the command line, but it also creates a build dependency between my app and helper lib. This guarantees that helper lib is available when my app is going to be linked. The relationship between application and library is defined in just one place, exactly there in the last line. And I think that's quite convenient. Passing variables down to subdirectories in QMake projects is a chore that usually involves include files or avax. In CMake, you can set variables on the subdirectory parent level. Like here, we set the variable source file to the value helper.cpp, and this one is available within the helper lib subdirectory and the application subdirectory. These variables are visible there, but changes to those variables in child subdirectories, like we do here, we set source file within the helper lib subdirectory to the value broken.cpp. Those changes here are local to this subdirectory and all its children. Changes to this variable are not visible to the parent and not visible to any siblings. Now let's look at the QMake feature that's not automatically converted by QMake to CMake. And to this point, all we saw is automatically converted. But QMake extra targets are not. This example here, which is a little bit longer, adds a make target called format to the project. When invoked, make format will run the clang format tool on all source files and then eradicate all code review discussions revolving around coding style. It will just apply the WebKit style on all the files that are in the sources variable. In CMake, we don't have a variable that holds all source files, and we first have to retrieve the list of source files from the target. Well, we could, of course, put the source files into a variable first and use it here and later on here, but we can retrieve the source files from the target by querying the sources property. Then we call the function add custom target, give it a name format, specify the command, tell it to go into the source directory, and run the clang format tool on our list of source files. We specified the verbatim keyword here, which ensures proper quoting of the command. It's highly recommended to always use the verbatim keyword. It should always be used. QMake extra compilers are another QMake feature that's not automatically converted by QMake to CMake. This example adds a rule to transform a protobuf description file to C++ source code. In order to do that, we run the protobuf compiler, the protoc tool, on all files specified in the protobufs variable. This one here. Here we specify addressbook.proto, which is then converted using protoc. The resulting C++ source files are stored in the sources variable. It's this line here. And QMake picks those up and compiles them, and then they are linked into the application. Protoc reads files from the source directory and generates C++ sources in the build directory in out_pwd. And finally, we need to link against the protobuf library itself. In CMake, where the project description is done in an imperative way, we have to write some more code. Our goal here is to write a function that we pass a target to and a .proto file that we want to add to this target. How would we implement this add protobuf function that's called like this? First, we construct the output file name from the base name of the file, the input file. Base name is called the stem in CMake terms. Set the out file name variable to what protoc will produce. Then we call add custom command, specify the output and the full command. We point protoc to the source directory and the build directory and the input file name. Again, we pass the verbatim keyword to ensure proper argument quoting. The function continued. What's left to do is we must add the generated source file to the target that was passed in the function call. And that's how we use it. At protobuf, we pass the target to it and one function, one .proto file. We could alternatively write a function that takes a list of proto files. But the question arises, where do we place such code? In QMake, we would have used pre-files or PRF files. In CMake, one good place to encapsulate helper function is a CMake module. we can create a CMake subdirectory in the root directory of our project, and then we move the implementation of our add protobuf function to a new file, protobuf support.cmake, and we add the path of our new subdirectory to the CMake module path variable. And after we have done this, we can call include with just the module name, which is the base name of the CMake file we just created. And the add protobuf function is then available. Using CMake modules for helper function is a nice way to keep your project tidy and maintainable. Something completely different, installs. QMake to CMake generates basic installation commands. This provides some scaffolding to refine upon. This example shows the installation of an application target in QMake. The executable is installed into my app. In CMake, the installation is done with the install command. And this also installs the executable, but we never specified where to install to. So where does it go? We have several installation destinations. CMake install prefix specifies in CMake, the installation root directory or the installation prefix is controlled with the variable CMake installation prefix. With that installation prefix, artifacts of different type go to different places. There are several types: runtime for executables, library and archive for shared and static libs, private header and public header for header files of a library. By default, executables are placed into bin, libraries into lib or lib64, header files into an include subdirectory of the installation prefix, and so on. The default names, libbin, etc., are set in the corresponding variables CMake install bindir, CMake install libdir, and CMake install include. So to install the executable of the my app target directly to the installation prefix, we specify runtime destination dot. To actually install the project on the command line, you run CMake --install on the build directory, and you still can override the installation prefix you specified in the initial CMake call. Alternatively, you can run ninja install. CMake installs command is a Swiss Army knife of installation. You can install targets, files, and directories in a platform-independent manner. You can define components and with them install just parts of the project. You can modify the rpath or run path of binaries on installation. You can run platform-independent CMake scripts on installation. And you can export library information for public consumption, meaning a library you wrote can be easily consumed by other CMake projects. And finally, you can install the so-called runtime dependency set of a target, basically the external libraries that are needed to run your project. For Qt projects, please have a look at our Qt-specific CMake deployment API. Keyword here is Qt generate deploy app script. That was quite condensed, but if you need more information and if you want to convert a more complex QMake project, then you probably will need more information. So what to read or watch next is, for instance, Qt's Getting Started with CMake documentation page, and I highly recommend watching Craig Scott's video from last year's World Summit, developing Qt 6 projects with CMake. Here's the link. And also his book, Professional CMake, a practical guide, is a cornucopia of CMake wisdom. Thanks for your attention.